So this lesson is on projectile motion with angles. And if we look at our objective 2 and our unit 1A overview, we've already completed the first 3 sub-objectives. So today we're going to focus on solving problems given non-zero initial conditions in both the vertical and horizontal using kinematic equations, and qualitatively describe the effect of air resistance on falling objects or objects in with projectiles, objects in projectile motion. So first we want to neglect air resistance. And we want to see what we can deduce about the object's motion when in this projectile motion where there's a non-zero initial vertical velocity. So we may start let's start here and say, well, the one thing that's different now is that there is some velocity vector that is not strictly a horizontal velocity. So this is our initial velocity vector u. And I say it's a vector because there's an angle, right? There's a direction. Now, they're always vectors, but we have to, in this situation, identify the different components of the vector. So that means we have to identify a horizontal component, which is drawn right here, and a vertical component, which is right here. So this is our u of x, and this is our u of y. So that's the main difference about what we will see. But there's a lot of more information we can extract from here. But in order to do that, we need to kind of identify kind of our the constants that exist here. And that would be something like a of x, which we know if there is no air resistance, that it is 0, and our acceleration in the y direction is just g. So it's negative 9.8 meters per second squared. That negative is super important now because our object is now going up and then down. So as the object's vertical velocity, or as it travels in this motion, the vertical velocity is decreasing 9.8 meters per second every second until it reaches some 0 point. So I might also recognize that at the very top, we're going to have a v of y equals 0. And now it's also important to note that I use v of y because there is an initial velocity at the beginning, and that might be my final velocity. But that could also be an initial velocity if I say, well, what if I just look at this portion of the fall? If I look at only the first portion of the fall, this would be v of y. But it's possible that it could also be u of y depending on your time frame or the distance that you are looking at. So let's look at one of the distances. And this is a vertical displacement. So we'll call this s of y, but this is our maximum height. There are other vertical displacements throughout this whole projectile motion. And depending on our time frame, we might be able to find that out. But we do know that it's easier to find it out here because we have a 0 value in our velocity. And usually, right, zeros are good for us with the kinematics equations. We also know this is halfway through the object's motion. So I might be able to also say this displacement here that goes all the way across is our like s of x. I'll say maximum, right? That's our full range. But I can also break it up into 2 separate parts. I can break it up into here and of course the other side. So this is just 1/2 times s of x max. Same thing over here, 1/2 s times s of x max. We know this. We also know that if there is some time, right, which occurs, let's say t equals 0 here. Let's put this in blue. So right here, t equals 0. And let's say here is just t equals, I'll just do capital T. So like some capital T time has passed. We also know that similarly, this would be t over 2, and this would be t over 2. If there's no air resistance, we also know that the final velocity vector would also equal u. So u is equal to v in this case, because due to symmetry going on with the world and acceleration and things like that, what speed it goes up with, it will come down with if it lands on the same horizontal surface. So that being said, I know that this vector Let's draw some final. Let's give it actually I got purple. It's got a downward and a rightward velocity components in which this downward is equal, so u of y is going to be equal to v of y here. That's something to note if there's no air resistance. And we also know that u of x is equal to v of x, but that's because no matter where you are, u of x is always equal to v of x. So we have, I think, all the major points we have. We know that if we have a total time, the halfway point to the time will also give you the halfway point in the horizontal displacement. We also know that halfway through this motion is when the object will have its maximum height, and at the maximum height, it will have a velocity, vertical velocity, I'm sorry, of 0. It still has a horizontal velocity, which is still u of x, right? So that's still the same. We would have to find out the initial vertical component of velocity and the initial horizontal component of velocity to kind of help us move around this. Now, there's nothing technically new, in quotes, to this. There's just problem-solving techniques. And in this projectile motion, there's a few ways you can look at it. And so we can look at it, I'll show you the windows that we can. We could look at it as the whole projectile motion. If the question is asking like how far did it travel, you can use just the initial point here, right? And the final point right here, and you can use those two values to solve for that. But sometimes it's easier if you break it up into two sections. The first half, because we know we have a final velocity of 0, or somewhat little weird is I like the second half. Because if I look at the second half, then my v of y is actually my u of y if my time frame is from the maximum height point to the end of its fall. And we know that when we have u of y, or u to be 0, our kinematics equations of like specifically s equals ut plus 1/2 at squared turns into just s equals 1/2 at squared, and we don't have a quadratic, and we don't have to solve through any annoyances. So the more practice we have with this, the better we're going to be able to solve these problems. Similarly, if we include air resistance, so if we do not neglect air resistance, what happens to the path of the projectile? Good news, there's no quantitative calculations to this. It's only qualitative, so you just need to know how does the object travel. Well, air resistance slows down the object's motion depending on its direction of velocity. So it may start off, let's do purple. It may start off right with the same vector, but now its vertical velocity is actually decreasing faster than before, and its horizontal velocity is decreasing where it wasn't before. So it's going to start slowing down. It's going to end up kind of hitting a point, and then it's going to curve. That might be a little too much. It's just going to curve, yep, and then slow down. Kind of like this, where due to the air resistance affecting and decreasing both the horizontal and the vertical velocity. So that's the qualitative drawing of an object in projectile motion with air resistance. And we can move forward. So now, but the good news is we don't do calculations with that. So let's go back to here and let's do some calculations. So we've got this road trip bridge problem. So the first thing I want you to do is I want you to watch this road trip video. It's a stupid clip from a stupid movie, but it's fun because you actually get to see, again, how movies either support physics or completely just kill it. So I want you to watch that video and try to identify any of the values for initial velocity, the distance, things like that. Unfortunately, they're in miles per hour, so I'm going to help you convert that. So we're going to do miles per hour. We're going to convert it to meters per second. And I would like you to also draw a picture of the problem, including any quantities that you know. So go ahead, pause this video, go to the details section of this YouTube video, and you'll find the link to this road trip bridge problem video. And I will see you in a second. So I've drawn my diagram based off of the information that they said in the clip. And even though, sorry, I had to make you watch that. I feel like I need to update that clip. But here we have a 30-degree incline. The other incline, the other side is gone. So we're just gonna draw it like a flat side on over here. We said they would need to hit 75 miles per hour, which is about 33 meters per second. I don't think they would do that, so I'm going to set my U of, oh, that's not my U, that's just my U of Y. That's just my U. I set my U, initial velocity, to be about 30 meters per second. Let's just, round down a little bit. I have my acceleration, my y direction is negative 9.8. I have my acceleration, my x direction 0. We saw it first. He said it was 10 feet, and then the bridge broke. So I was just like, well, let's just double it, 20 feet, which is about 6 to 7 meters. So just on the easy side, let's say that's around 7 meters. So we already said this is about 30 meters per second. That's around 7 meters. So my horizontal displacement is going to be 7 meters. My acceleration in my horizontal direction is 0 meters per second squared. We don't have time. We don't have our height, our s of y. We don't have our u of y yet. We have our a of y, which is negative 9.8. And t. Actually, there is something we do kind of know, but it really depends on what we're trying to solve for. If we're really just looking at, let's just look at from point A. So let's identify where point A is. Here's point A. And let's say this is point B. If we're only looking between those two, now there's kind of some issues here with this diagram in that A and B are actually on different heights. So let's just fudge this a little bit because it's going to help us out. And we're going to say that it lands pretty much on the same height. There's already issues with this problem, but we're just going to try to adjust things to see, does this even sound any bit reasonable? If our numbers get semi-close, then we can say, okay, maybe it's possible. If they're way off, then this doesn't matter. Me fudging the numbers doesn't matter. So this is actually saying that my total change in my displacement, my vertical, is 0, because from point A to point B, I have not traveled up any distance from here to here, right? That's a flat line. Now, if I wanted to find my height, my maximum vertical displacement, then I'd have to kind of change some numbers around and say I would change where my points A and B are. But let's do it this way and see what happens. So first things first, like whenever you have projectile motion with an angle, you need to calculate the components of the horizontal and the vertical. So for our horizontal, and this is in our data booklet, this is just u cosine theta, where my vertical is u of y is u sine theta. And we said our u is 30, so this is 30 cosine of 30. And then this is 30 sine of 30. Let's do that calculation. And make sure you are in degree mode. So go to mode and make sure you have degrees set. So 30 cosine of 30 is about 25.9 meters per second. And 30 sine of 30 is about 15 meters per second. So before I move forward with putting in these numbers, there's a mistake I made, so I kind of had to cut myself off. And I wrote that this was equal to 7 meters. But the question is, does the car make it across the river? Show all work that is needed to determine the answer. And if it does make it across the river, then it would land like here, right here, oh, there it is, or here, or here. It'll land some distance greater than 7. So actually we don't know what this is. But we do know that in order for it to make it across the river, that it needs to be greater than or equal to 7 meters. So that's an update I wanted to make. So I have my values of 25.9. I need to round it up, so it's 26 meters per second in my x direction. And I also know that since we're assuming no air resistance, that our final velocity is also 26. And then for a vertical, it's 15. Oops. And I also said that if we're landing at the same height as our original height, then we know that our final velocity should be equal to our initial velocity, except going in the opposite direction. So this is actually negative 15 meters per second. And I think I fudged that up here as well. So this right here, there's a negative right there. I added that in. That's because it's going up. So it's in the beginning, it's going up, so it's positive. And then at the end, it's going down, so it's negative. And we don't have time, and that's what we need to solve for. So we'll need to choose which sides of the equations do we want to use to get to time. And usually in most projectile motion problems, the vertical is the easiest one because we have a lot of information. So let's use this data to solve. I have my A, my V, and my U, and my S, and I want to solve for T. So there's a lot of actually avenues I want to use. I don't like S equals ut plus 1/2 at squared because then that turns into a quadratic. So I'm going to go with the basic V of y is equal to u of y plus a of y times t. And V of y is negative 15. U of y is 15. And then plus my a of y is negative 9.8 times t. So I subtract 15 over, and I get this, which is interesting. This is very similar to that graphing problem we did last class, where the total change in vertical velocity is twice its initial velocity because it goes up 15, or rather, it starts at 15 and goes down to 0 and then back down to 15. So it's like passing through the number line. And we can find time out this way. So 30 divided by 9.8 is 3.06 seconds. So that's a lot of time in the air. It's a lot of time in the air. 3.06 seconds, 3.06 seconds because it's the same for both. So I'm going to take that value and I'm going to solve for s of x. Again, there's a lot of options to take, but it's all going to end up into this because we know that plus 1/2 at squared cancels out because a is 0. So u of x is 26 meters per second. Time is 3.06. And so s of x is equal to some huge number. 26 times 3.06. You might be saying, wow, are we wrong? No, the movie is really problematic. Even when the guy says, with physics, I'm always sure, he was not sure at all. He would have gone 80 meters if this is the information we were using. And they only needed to go 7. So even with air resistance, even with the kind of fudging that I did with these like similar height points, there's no way this math would have worked out. So that movie goes on one of the worst physics problems ever made in a movie. Well, that's it. We've worked through one type of problem in this video. The practice problem is going to be another type, and there's a lot of different avenues to take when solving these problems. So the more practice we get with this, the better and more comfortable we are going to feel about projectile motion problems. I will see you in class.